And in 2024, he joined MNEXT as the new lecturer for the research group Renewable Energy Carriers. In his research group, he will focus mainly on educational and research projects, of course, but spanning three different research lines, namely hydrogen, e-fuels, and iron fuels. And I think that concludes my introduction for you. I think the rules are clear for everyone. And then with further ado, I leave the floor to you, Saleh. You can start all out.
Just to check if the recording is ongoing.
Working. Yeah, I see. Started by Wendy van Rijsbergen. I see the recording.
Okay. Yeah.
So you can take it away.
Yeah. Thanks, Sander. Thanks for the introduction. Sorry, I just. Yeah. Hello, everyone. Welcome to this Launch and Learn organized by the MNEXT. I'm glad to be here and have this opportunity to talk about my lectorate, Renewable Energy Carriers, as a brand new lectorate at MNEXT. I hope you enjoyed the presentation. So this is a short agenda for this presentation. I start with the introduction of our Center of Expertise, MNEXT. I will introduce my lectorate and also the main focus of this presentation, which is about research line and focus areas. As Sander mentioned, hydrogen, iron power, and e-fuels. And if time allows, I will also mention a few of our ongoing projects and followed by Q&A. So, Center of Expertise, MNEXT, basically, stand for Material and Energy Transition. This is a kind of the topic that all the lectorates, which here you see the list of 7 lectorates, basically working on that. There's two main parts or two main wings, the material side and the energy side. I'm connected to the mainly focus on the energy part with the lectorate of smart energy. And we also have other lectorate that mostly work on the kind of bio-based materials. But of course, in the project, we have a quite collaboration. And also I should mention that the MNEXT is a joint venture between the Hazard and Avans. So about my lectorate, Renewable Energy Carrier lectorate, I mentioned this is a new lectorate established in LA this year, 2024. And our mission is basically we are aiming to create a kind of robust, sustainable, and circular energy system that maximize the renewable resources usage and also reduce the basically dependency on the fossil fuel and CO2 emission fuels. And we do that via researching basically and focusing on generation, usage, transportation, and storage of clean energy carriers and fuels, and how they basically take a role in the new energy transition and new energy transition ecosystem. We're doing this basically with the collaboration with the other regional businesses. We are a hub, so we are connected to the region, but also other educational institutes and also international institutes. Some of the main key aspects that we are investigating and researching with regard to the renewable energy carriers, you see here technical developments. We need to know what kind of carriers we want to develop. We need to know the specification. System integration is very important. Energy carriers are part of the bigger energy system that they need to be well integrated. Economy. That need to make sense, the financial wise, basically for the off-takers and for the clients need to have a kind of reasonable economy as well. Infrastructure adaptation and also regulatory aspects, how to use these new carriers as part of the energy system. This is my new team. I would like to introduce them. Renee, Hubert, Ali, Jeroen, and Sander. And here I would like to welcome them, and I hope that basically we can together do what we envisaged. And just to mention that we are also expanding, so we are also hiring new people. I don't know if the students are present in this session. We're very welcome to approach us if they have any ambition to work in this area. But why we are doing this? So what's a grand challenge that basically our lectorate is aiming to tackle? I always start with these slides. It's a nice slide that basically shows the historical of a CO2 concentration, CO2 level, and temperatures in the atmosphere. If you look at it, this is for the over last 5 million. If you see, there's a nice correlation between the CO2 level and also the associated temperature with it. But you see also something which is a bit, not a bit, is quite alarming. And that's in the recent decades, in the 1950 and onward, the amount of CO2, the level is just significantly increased. And now we are at the 424 ppm. This is the June 2023, I think is more than this now at 2024. And if you look at the history, the last time that basically this CO2 level exists, it was like 3 million years ago. And if you look at the temperature associated with that, it's like +5 degrees higher than what the kind of average temperature we had pre-industrial time. At the moment, we are like a 1.5 degree anomaly, like an increase compared to that time. But there's a big but. This is just basically the tips of the iceberg, because historical record, if you a bit more detailed zoom on that historical basically trend, you see that there is a time lag, 10 to 50 years between these two, and this will be then this showed that basically, I hope not, but was to come in terms of the impact of the basically CO2 increase in the CO2 concentration in the atmosphere. And we all know, we agreed, basically all the politicians agreed in Paris 2015 that they want to limit the temperature rise to 1.5 degree. And to do so, you need to limit the CO2 level to 450 ppm. But can we make it? That's a difficult question, because if you look at the trend over the last few decades, we were at like 330 ppm in 74, and 2023 we are in 424. And if you compare it last year with this year, we are at 427. So it's like a 3 ppm increase in 1 year. And to get there, if we go with the same trend, we just have like a few years, less than 10 years. So I think our carbon budget is somewhere between 300, 400 billion ton of CO2, which with the annual production of 40 billion, yeah, it's we are in the kind of quite a critical moment. So how we can limit this? I mean, the question, probably the answer is not difficult. We need to go to renewable sources, specifically on the energy system that basically contribute significantly to the CO2 emission. So we need to go to the renewables, and we need to go for a significant amount of renewables, not the little ones. One study shows that if you want to stay below 450 ppm, we need to have at least 30 terawatt, like a 30,000 gigawatts of renewable energy power. I just try to translate this to what does it mean in terms of solar and wind. I will not go to detail. I will share the slides. You can check it later. Basically, if you want to go to this amount with the solar, you need, like, if with the lowest estimate, highest estimate, somewhere between 7 to 10 times of the kind of Netherlands size solar power plant. And if you go to the offshore wind, basically that means almost 70 times of Netherlands, basically the area that you need offshore wind. So we're talking about a significant scale. But can we make it? Of course we can make it. The solar, the potential for the solar is just abundant. So if you look at the here in the left side, this map, this is a global solar radiation intensity, over the world, over the globe, and here is the global distribution of energy demand, basically consumption per capita, you see there's a potential, but there's a mismatch in terms of location. So we have mostly the solar area, solar mostly intense area. You can make the same also for wind in this part of the world, but we have the demand mostly in this part of the world. So this shows there is a kind of mismatch in place. And that's also the case for the time, because look at these graphs below. We have a lot of production over the day. We don't have a kind of solar radiation in the night, and that also on the seasonal basis. So we need some kind of medium to fill this gap, both on the kind of spatial, but also on the time. And that's what we believe that energy carrier or clean energy carriers will be able to fill basically this gap. So with this, and maybe also we're talking about clean energy carriers. I think the electricity is a kind one of the most versatile and the kind of type of carriers. And I think we should use electricity as much as possible. So use electricity where it's possible because you don't have any losses, any conversion losses. And you see at the moment for the built environment, heat pumps, they use electricity. In the kind of light electric vehicles, we use battery-based vehicles. So those are a good initiative, and we should do it as much as possible. But there's an issue with it. If you look at the Netherlands, if you look at these maps, the red area shows the areas that electricity network is already congested, it's overloaded. So there's not really any capacity anymore for the new connection or even new kind of fit, but also the demand side. So we have an issue at that side that we need to see how we can resolve that. And also for the certain applications like high temperature industry or heavy transportation or aviation, you need a more kind of type of energy carriers, more dense energy carriers, which electricity is not at the moment not able to fulfill that. So electricity is good, but we need a kind of also other type of energy carriers like hydrogen, synthetic fuels, or iron power or iron powder, basically to fill this gap. And that's why or my lecture basically is going to focus on. So here is the main or three research lines we are at the moment working on. The green hydrogen, we are focusing on production, use, transportation, storage of hydrogen, grid integration, and type of flexibility, operation of the electrolyzer, because we are dealing with the dynamic and kind of variable type of load. Specific application of the hydrogen, for example, in steel making, or derivative pathway. So there is a lot of different type of hydrogen derivatives that we would like to see what basically, how does it look like? We also have one interesting energy carriers. That's basically something that we see the connection with the region, and that's about iron powder or iron power, basically. There's a lot of parties working on this in this region, and I think this would be a kind of valuable also research line for us to contribute to. Specifically in this research line, we are looking at the larger scale application of this carrier for the energy storage and transport, but also we want to look at the more kind of local usage of this carrier, for example, in business trains or neighborhoods as a seasonal storage. And the last one is the e-fuel, which we would like to look at basically the synthetic fuels and how they could replace the conventional fossil fuels. So about if I start with the hydrogen, you know, it's become like a holy grail. Everyone talk about it, and also that the whole climate scenario also shows that the hydrogen will take an important role in the future energy system. But if you look at what kind of role that hydrogen can take at the moment, also in the future, here is the view that I basically put it here as a clean feedstock. You know, we use hydrogen at the moment for as a feedstock for a lot of chemical processes like ammonia production, or as a clean fuel. We can use it basically at the moment for the mechanical kind of thermal application. We use basically fossil fuels. Hydrogen can replace them. For example, here use methanol for the container ships. As any carrier, I mentioned replacing oil, gas, coal. You know, you have a hydrogen pipe basically can replace those, or as a storage medium. That we can use it basically on the daily, but also on a significant scale, like on a seasonal scale, use it as a storage. Look at the salt caverns or basically all the gas fields that can be repurposed as a seasonal scale hydrogen storage. If you look at the also hydrogen system, hydrogen system has a kind of different parts. We'll just a bit we are touching these parts. It starts from the production, then we have a conversion, transport, storage, consumption. If I start with the production, hydrogen comes with basically with the different shades or colors. Probably you heard. This graph shows the colors based on basically the feedstock that you use for generating the hydrogen, but also the type of basically energy. Is it renewable? Is it heat? I don't want to explain all of them, but like a pink hydrogen basically is from the electricity from the nuclear power. Yellow one is also electricity, but it's water-based, but from the basically fossil fuel electricity. The whole green shades that come from a kind of different technology, like a water electrolysis, thermolysis, sorry, and photolysis, or maybe biomass and biogas based, which basically via the gasification or steam reforming. And also more the conventional type of hydrogen, which we call them gray hydrogen, which basically mainly based on the natural gas and via the SMR and ATR process. But we can also basically capture the CO2 from the gray hydrogen and make the kind of blue hydrogen. But here we mainly focus on the green hydrogen and specifically on the kind of water electrolysis hydrogen in our research group because it's basically it's CO2 free and we can use the water for generating hydrogen. So the basic principle, I think most of you knows, we just use electrolysis to split water to hydrogen and oxygen. There's a different technology for doing that. I'm not mentioning all of them. I just put the three ones that basically are in the market at the moment: alkaline, PEM, and solid oxide. Alkaline is a well-known technology. I think we have an installation in Norway probably with a 70, 80 years history. So it's a mature technology. And it's a low cost. You don't use a very kind of rare or type of materials. And it's widely used in industry, I think, for years. But more kind of on a lower TRL, we have a PEM. PEM basically stands for proton exchange membrane electrolysis, and they use a solid polymer electrolyte basically to carry hydrogen protons basically from the anode to the cathode. And it's a quite efficient, has a high current density, and it's capable to basically to ramp up and ramp down quite easily. If you compare it with, for example, alkaline. That's why you see it more and more application of the PEM electrolyzer with the renewable energy sources, because it can basically react quickly to the network dynamics. But also we have a solid oxide, which is more kind of lower TRL at the moment. And it uses solid oxide or a ceramic electrolyte basically to conduct oxygen ions. And then the working environment is quite, it's a high temperature, so somewhere between 600 to 800 temperature. But then in that environment, the efficiency goes up quite a lot. But of course, you need a source for creating this high temperature. So in the type of industry that you already have this waste heat, it's good to use a solid oxide compared to other technologies. Here is the basic functioning of this electrolysis that they mentioned. I don't want to explain them, but here you see basically how the hydrogen and oxygen evolution basically reactions occur. But this technology also comes with the challenges. We recently started a project, we call it HyPro, which in this project is a national project in the Netherlands. We are looking at how we can improve the performance of this technology, of this electrolysis. For example, for the alkaline, we need to increase the density, because at the moment we have them in the kind of quite bulky, because of the very low current density. So that needs to be improved. but also use a non-PGM catalyst. This is kind of a type of rare material that make it expensive. So see what kind of alternative catalyst we can find. If you look at the PEM is more critical because we use a lot of radium. So there is a lot of research ongoing how we can decrease the radium loading basically in the PEM electrolyzers and find more low-cost, cheaper catalyst. Then there's quite a research about using the PFAS-free basically membranes, for example. On the solid oxide, all comes back to increasing the lifetime. I mentioned we are working in a kind of quite a high temperature environment, 800, 1000. And then you need to basically be sure that the type of material you use, that they can keep their mechanical strength and structure. So a lot of research ongoing how we can increase the lifetime of the solid oxide electrolyzers. If you on the production side, if you look at the current production, this might be a bit old, 2021, but we are at the moment producing around 100 million ton gray hydrogen. Mainly, it's a gray hydrogen at the moment, which a lot used as a kind of feedstock for the industry. But the projections, basically, there's a different projection. This is a projection that we need to go to the 500, close to the 500 million ton hydrogen by 2050 if you want to basically achieve what we have already imagined for getting kind of CO2-free energy system. And a lot should also comes from the renewables as a green hydrogen, or also more kind of transition solution, which is a kind of blue hydrogen. So we see that there is a kind of significant task ahead, basically, to be able to generate this amount. I here put this simple calculations, what this means in terms of, for example, power that we need to generate this amount of hydrogen. For example, here for 300 million ton of green hydrogen, I calculated that we need almost 8.1 terawatt of variable power, which is solar or wind, which is 6 times more than the install capacity, the total install capacity of renewables at the moment we have globally. You can later look at all the kind of the detail of the calculation. Due to time, I will skip it. Also, regarding the cost of the hydrogen production, at the moment, the gray and blue basically are in the kind of range of $1 to $3 per kilogram, and the green one is quite high because of the basically technology is not mature yet. The green power is expensive, but we need to basically decrease that if we want to create a kind of stable offtake or market for the green hydrogen. This has to decrease. And basically there's a projection that, like solar, this might also happen. So technology basically advances, there will be supporting policies, and there will be a market basically to help to reduce the price of the green hydrogen. On the demand side, there's I mentioned at the moment we use like close to the 100 million ton hydrogen, a lot as a feedstock for the industry. But the projections basically shows that we have to go to a significant scale, and here you see how it will basically diversify on the demand side, on the off-taker side. So you see that the industry still keeps the big chunk of the hydrogen and green hydrogen. But then you have new players like mobility, mainly a long distance type of transportation that you cannot use a battery, or maybe new industries, for example, for steel making, you need a green hydrogen to make a kind of green steel, or for the heatings, for the high temperature heating, or also for the power generation. So this is the kind of new demand, new off-takers for the hydrogen and green hydrogen that will come in the next 2 or 3 decades. If you look at the storage, like in natural gas, there's a different way of basically to storing hydrogen. Here I put some methods like compressed hydrogen, basically gas, which still is one of the cheapest basically when we are talking on a kind of short term on a smaller scale. but you could go also for longer term seasonal type like a salt cavern. As I mentioned, it's one of the cheapest when you go to the large scale. But there's also other methods like liquid hydrogen that yet is quite expensive. It's mainly good for the kind of short distance, low scale type of hydrogen storage. Ammonia is it's quite known, but yet also still expensive, mostly because of a lot of energy that you need for the cracking of the ammonia to extract hydrogen. On the transportation method, that depend on the two main factors. It's a distance and load. For the short distances, I think like it's very similar to what I mentioned in the storage, you can still basically use a compressed hydrogen gas tracks or local pipeline. But when the distance and loads increase, then basically you need to go more for transportation or transmission pipes or transportation pipes, or maybe on the intercontinental, basically displacement of hydrogen goes to the ships, for example. If you go to hydrogen derivatives and carriers, here I put three: ammonia, liquefied hydrogen, and liquid or organic hydrogen carriers. Ammonia is known. We have an infrastructure for the ammonia, I think, for decades, and it's well established, so can be a kind of a potential carrier for the hydrogen, but there's a problem with it. Ammonia is toxic. And still, there's quite a strict regulation about basically moving around, especially on land for the ammonia. And also, as I mentioned, the cracking hydrogen, you need a lot of energy for the cracking. Liquefied hydrogen, that's also another solution, expensive, but there's also well-established technology at the moment. The problem is you need quite a high energy requirements to go to the cryogenic temperature, basically, that you need to liquefy hydrogen. And you also have a lot of losses, somewhere between 0.5% and 1% of the basically total energy per day you lost via the boil off of the liquid hydrogen. Liquid organic hydrogen carrier is a quite interesting one. The TRL are very low at the moment. There's a lot of research ongoing, which basically you use some kind of chemical compound or kind of materials to bound the hydrogen molecules to that. And you can basically, via the hydrogenation or dehydrogenation, basically move hydrogen to the location that you want. But again, this is a low TRL, and still a lot of research is ongoing about how LOCH could take a role. So that was very brief about the hydrogen. I'll also be brief about the power line. I hope more brief. The second research line is about the iron power or iron powder. I mentioned this is interesting because there's a lot of party basically in the Brabant and in the area that are interested and working on that. The basic principle is quite simple. So we have a renewable energy, we make a hydrogen, and we use that hydrogen to reduce the iron oxide. And by doing that, basically we create iron powder, and we move that iron or transport that iron to the location that we need, to the demand location, and we oxidize the iron. And by doing that, we either generate heat, or on a kind of wet dry, we generate hydrogen, and then we use it, and we create rust or iron oxide, move that, transport that again to the original location, to the supply point, and this cycle can reiterate for many times. It's a very safe, non-toxic, non-explosive carrier, which with quite a high efficiency. I mentioned you could basically do the oxidation in two ways. Either you could just burn it and generate quite a high temperature heat, 800, 1000, and then use it for whatever application you need. But also you could use a kind of cycle, we call it a wet cycle, which basically you oxidize the iron via the steam, and you can generate pure hydrogen. This is a technology at Eindhoven University are working on it, solid team. We are working with them basically to see how we can contribute to this interesting cycle. So based on this, this is the kind of main areas that we are at the moment looking at it for the iron power. So we are looking at the larger scale application of the iron powder, you know, for moving or displacing energy from over the long distance. But we're also looking at how we can use the iron powder in a more local, for example, as a storage medium or seasonal storage for example, for dealing with the network congestion. And of course, as also Applied Science University, we like to basically create a knowledge base on the iron powder at Avans as well. And the last one I mentioned our research line is the e-fuels. So e-fuels or synthetic hydrocarbons basically created to replace fossil fuels. And in this first line, we try to see basically we explore these synthetic fuels. If you're talking about renewable fuels in general, we have two main basically options based on the feedstock that you use: the bio origin, the biofuel or biogas. I think quite known on the EU is quite well regulated. So this is not our focus. We have our own opinion with about it. You can ask me. We can have a discussion. But our main focus would be on the non-bio basically fuels. Also in the kind of RED 2 and 3 is known as a renewable fuel from non-biological origin, and which we use mainly hydrogen and CO2 basically as a main feedstock to generate these fuels, mainly via the famous Fischer-Tropsch process. And our goal is also basically execute or build a pilot plan with our partners to generate these e-fuels. I think I'm running out of time. I will be very brief about I think I mentioned our research lines. Our ambition is of course, we want to establish ourselves as a leading knowledge partner in the region with regard to the hydrogen and clean energy carriers in the Brabant, in the South Netherlands with other partners. We want to link the research and education. We want to basically also bring hydrogen to the education at Avans in other academies, and also work with the local company, government, and knowledge institution on this. Like I put some names here: Hazet, IRIS at the TUE, Hanseschool, Han, Saxion, and we are also basically aiming to establish an electrochemistry lab with other lectorates at Avans, and establish, as I mentioned, a pilot plan for iron power and e-fuel. Sander, I don't know, do I have time or should I stop? Because I want to just show some ongoing projects.
Yeah, I think there's 10 minutes left officially on the counter.
Okay.
There are 4
I will
questions.
make it just in 1 minute so I can finish it. That's okay? Yeah. So we have a few ongoing projects, a lot part of the Groene Vermogen. First one was a HyPro. I think I mentioned it, that mainly focus on hydrogen production. We also high use, which look at the more kind of demand side and use of hydrogen. Here we specifically work on the kind of hydrogen microgrid for the wastewater treatment plant. I think Sander is, as part of our electorate, is working on it. We recently granted the high success, which is mostly look at the social acceptance of the hydrogen and basically the market and the business models to make it work. And the last one, not the least, is a project that we recently have been involved, and it's about the green steel, how we can use basically hydrogen to greening the steel industry as one of the basically global pollutant of the industry pollutant. This was some of our ongoing projects, but I would love to talk further about that with you, but maybe in another opportunity. That's it. Thanks, Sander.
Yeah, no problem, Salet. Thank you. Yeah, thank you for this very comprehensive overview of your lectorate and the plans and the visions that you have. I saw 4 questions coming in, and I think we're going to run them down from chronological order, starting with the question from Yide Gau, if I pronounce your name correctly. And he asked, to what extent is nuclear energy currently in the scope of renewable energy discussions and research? Are there particular challenges of integrating it into the energy system and grid?
You mean the nuclear energy?
Yeah.
Yeah, there's a lot of discussion, probably also you heard, about the nuclear energy and application of the new nuclear energy. We believe or I believe that nuclear energy can have a role in energy system, because if we want to reach zero carbon energy system by 2050, would be very difficult to achieve that only by solar and wind. And you need some reliable base source, basically, to getting there. Again, this is open for discussion, but we need to certain level, basically reliable base load to make electricity, basically for our energy system. If you want to connect it to the hydrogen, could be an interesting case also to make a pink hydrogen, for example. I don't know, there's a discussion of having a like SMR type of power plant only to generate hydrogen for the industrial clusters, like a Tata Steel, for example. But we see a role, but we also understand that from the social acceptance, and yet a lot need to be done to make sure that it's safe and it will remain safe source of electricity.
Yeah. Either did that kind of answer your question? I think so. Because with shortest, yes, I see thumbs up, so I guess that's a yes. Then the next question is from Martijn Sieverink, and he's asking, why do we need to produce all that hydrogen? Why not just electrify industry or transportation and or?
I think I tried to explain it, that we need a significant amount of energy, and this to decarbonize our energy system. And often you can't find those in the kind of demand location. So you have to go to the other part of the world. And if you want to move and transport those, those energy, you need some kind of carrier. And hydrogen could, we believe that can have it basically a role for as a storage and as a carrier to move these energy to the demand locations. But again, I mentioned use electricity as much as possible. If you think that you can do that, because then you don't have any conversion losses. And what's also happening now, for example, in the built environment, we use a heat pump with I don't know, efficiency of 400-500%, and no one recommend hydrogen for a built environment or for the light vehicles.
Yeah, thank you. I think that Martijn answered it. Yes, thank you for the answer, Saleh. Then the next one, keeping tight in time with the time, Willem van Liemt is asking, what is the daily loss of the best in class hydrogen storage today? Is it good enough to prevent H2 greenhouse contribution?
Yeah, I think we all know the risk that comes with the hydrogen, specifically also the contribution to the as a polluting gas. Safety and leakage protection is one of the important topics when you are talking about hydrogen. So there's a losses, of course, you can never avoid it, but also there's a lot of basically safety measures, safety regulations to minimize the leakage, to also basically not contribute to the greenhouse contribution. But as I mentioned, for example, for the liquid hydrogen, we have a lot of losses on a daily basis. So we're not recommending that storage. Maybe you should go more for some kind of more, I don't know, in salt caverns or in a depleted gas, with well protected, to also avoid, to basically does the storage function, but also avoiding the leakage.
Thank you for this very elaborate answer. Willem says like, okay, that's thank you. So on to the next one. Martijn has another question for you. Let me phrase it for you. Hydrogen storage on iron will be limited by the total amount of available surface area. That means there must be an upper limit to the amount of hydrogen that can be stored per volume of powder. Any idea how that compares to the batteries in terms of kilowatt hours per cube or kilowatt hours per kilogram? It's a very technical one, but technical matter.
Yeah, I think I can answer that. I think if you, I don't have that graph. I have seen it. I see it from people from TUE also showed it. No, the iron doesn't perform very well in terms of kilowatt hour per kilogram on a weight wise, but on the cubic, if you say kilowatt hour per cube, that's quite basically you can store a significant amount of hydrogen. I cannot give you a very precise answer, but I think what I had number I had in my mind with the 2 or 3 cube, you can basically store the whole thermal energy demand of one household. So I think Sander probably can translate that to the kilowatt hour, but that's what I have in my mind. So that's a capacity you can get with the cube. But on a kilogram, no, it doesn't perform very well compared to the batteries or other energy carriers.
Yeah, because of the high density of iron,
Yeah,
I guess. Yeah,
exactly.
Yeah, Martijn gives like a thumbs up. He will spam you for the numbers, but I think also Jobert Lutlage, since he's still one day at the TUE, will probably can be spammed for numbers.
I think you can
probably
has
them.
quite a discussion with Jobert about how iron powder perform in that sense.
Yeah, since
and
he's
what will be
also
the
leading
best
the
use
research
cases
line.
for that.
Yes, exactly.
Yeah,
we have roughly 1 more minute left on the timer. Are there any other questions that the audience has? Okay, let's wait. Maybe people are typing for a few seconds.
they can
maybe
just open up the microphone to speak. Maybe that'll be easier.
Yeah, everyone is forcibly muted. That's the problem. With this new Teams technology, I'm also a little bit behind. You can't open it anymore. Only you and I can do that, and Wendy and Ewout, I believe. By looking at the time, we're nearly finishing. Then I would like to thank you for this very elaborate talk, Sella, and thank you for all the efforts given. I think your research line is clear. At least to me, it was. So I hope everyone enjoyed. And then I would like to ask you
last
remark.
Remark. Please, this is my contact information, and you can find me at the MNEXT. Please come to me if you have any question on this, or if you want to discuss it. I'll be happy to do so.
I have one more remark as well, or ask if you can switch to the next slide, because officially I need to, from Wendy, I need to talk about the next Lunch and Learn. The next Lunch and Learn is on Thursday, October 10th, same time as today, basically 12:15. It's about bio-based wet cell, bio-based solutions for wet areas. It's by Mariana Kulho, researcher and coordinator at Bio-based Building and MNEXT. Basically, you can scan the QR code to subscribe to that Lunch and Learn. So that's all for today. Thank you for your time and attention, and see you maybe on the 10th of October. Bye-bye.
Thank you, Sander. Thanks, everyone.
Yeah, thank you, Salah.